Good afternoon, everyone. Thank you for joining us. My name is Katie Rowley. I am with the NOAA Central Library, and we are bringing you today our NOAA Innovators series in partnership with the Technology Office, which Tiffany House will speak about in a moment. But first, some logistics. You are muted. If you do have a question or something you would like to chat at me about, please use the question and or chat panel on your in your right hand little box here. We will be holding all questions until the end when the presentation is over, and then I will be reading those out to our speaker. We are recording this. And if you have to step away for some reason, or you would like to share this event with your colleagues after the fact, this will be on YouTube, on the library's YouTube channel after the fact. And I feel like I'm forgetting something, but without further ado, I'm going to turn it over to Tiffany to introduce our speaker today.
Hello, everyone. Happy New Year. This is our first NOAA Innovator Series presentation of 2021. Today, I have the pleasure of introducing the speaker and briefly describing the Small Business Innovation Research Program, or SBIR for short. The mission of the SBIR program is to support scientific excellence and innovation through the investment of federal research funds in critical American priorities to build a strong national economy, one small business at a time. This is a highly competitive program which enables small businesses to create innovative products and services that benefit the NOAA mission and is responsive to greater market demand. The technology you will hear about today is from BlackSwift Technologies, and it's available for phase 3. So if an agency wishes to fund a SBIR phase 3 project, it is not required to conduct another competition in order to satisfy those statutory provisions. Sampling the lower boundary layer of tropical and other large storms is both extremely useful and difficult. Previous efforts have demonstrated that targeted observations of this lower boundary level by UAS can provide extremely valuable data sets for improving forecasts and models. To continue improving tropical cyclone intensity forecasts, and increased use of targeted in situ measurements has been proposed. Increasing the number of flights per storm affords the ability to greatly increase the temporal and spatial sampling, allowing for improved models and forecasts. The largest single barrier to realizing this objective is the cost of the aircraft, and overcoming this obstacle requires a purpose-built system. Dr. Jack Elston is the CEO and co-founder of BlackSwift Technologies. BlackSwift Technologies is a UAS solutions provider focused on scientific applications. Dr. Elston received his Ph.D. from the University of Colorado Boulder. He has a strong background in conducting in situ atmospheric measurements from UAS and is intimately familiar with the issues associated with operating unmanned aircraft in hazardous conditions, having hundreds of flight hours around the world on systems he helped design. I'm very pleased to welcome Dr. Jack Elston.
Yeah, thank you, Tiffany. I appreciate it. Thanks, everyone, for attending. Hopefully this is of interest to you. So I'm going to get started here. I'll just talk a little bit about my company, BlackSwift Technologies. We're a small business in Boulder, Colorado. It's a great area to be, especially for atmospheric science. But we do a lot of different other things with unmanned aircraft systems. And one of the things that's the kind of a premise behind what we do is that it's really all about the data. Unmanned aircraft systems represent a very unique platform for being able to go get specifically in situ data, a lot better than things that are just located on the ground where you only get one point of data, or a satellite where you kind of have to look through the entire column of the atmosphere. It's very hard to pick out things by altitude. So unmanned aircraft systems are really just the platform. We focus in on the data, and there's a ton of different things that you can grab from unmanned aircraft systems. One of the things that we focus on is atmospheric science, and that's kind of what we'll be talking about today. As far as our company, we've been around since 2011, and our founders have been operating UAS since the early 2000s. We've flown on a number of different phenomena. We've done everything from volcano sampling. We're designing this aircraft for use in hurricane sampling. We've done flown on tornadic storms. We've flown in the Arctic. And so we have a lot of different experience operating various different types of unmanned aircraft systems and designing systems specifically for these environments. And we've taken our experiences that we had in the field and kind of put that into our design. And I think that's one of the unique things about our company is, you know, we look at things like when you're in the Arctic and you're operating and it's -20 outside, you don't want to be taking off your gloves to assemble or pre-fly an aircraft. So we make it so you can do everything without doing that. So to kind of solve some of the atmospheric science problems amongst remote sensing problems, we have a product line that we put together, largely in part with help from these grants like the Small Business Innovative Research that Tiffany spoke about. We are pretty unique in the fact that we're one of the few companies in the world that design our own algorithms as far as control algorithms for the aircraft, our own avionics. We design all the boards. We do the airframe design itself. We design the user interface. So we kind of do the whole spectrum of everything for the aircraft. And while it's a bit of work to maintain all of that, it's nice because we have intimate knowledge of all the different aspects that go into unmanned aircraft systems. So we're able to make all these different custom changes and you know, respond to some of the needs, the demanding needs of scientific applications, because we can change things without having to wait for somebody else to do it. So one of the things I'll mention, this has kind of been our bread and butter for a while. This is our S2 UAS. So it'll carry a 5-pound payload. Packs down small enough that you're able to take it on board commercial airlines. And then it has a fairly large payload volume. We're able to carry a number of different payloads, and the payload's hot swappable. So in the field, you can fly one payload, take off that nose cone, and put another payload on. And this has kind of been the foundation for a lot of the stuff that we've done at BlackSwift Technologies for atmospheric science. And the reason why I'm mentioning it is it's driven a lot of the design work that you'll kind of see later and what we're doing with hurricanes, and the fact that we've put together very easy mechanisms for generating flight plans that are necessary for atmospheric science. You can see a couple of the examples here, and then you can string all this together with a nice script so that you're able to generate these fairly complex flight patterns specific to atmospheric science, and it's very easy to do and plan for beforehand. Now, we've also looked into a couple of different things that are required for flying beyond line of sight, or at least flying safely, one of the particular projects that we've been doing is looking at all the various subsystems, characterizing them, because a lot of these smaller aircraft, the components like servos and motors and things like that don't really come with any sort of manufacturer recommendation for the lifespan or maintenance cycles or anything like that. So we did a ton of bench testing to kind of see where those things failed, and then we applied machine learning to that to be able to see where things are starting to fail and be able to perform a corrective action before they fail. And we've also presented that information to the user and through our user interface through kind of a nice hierarchical setup where it's able to take a look at all the different things that might go wrong on the aircraft, categorize them as far as priority that should be addressed, and then just give them very simple messages that say, like, give the operator the exact information they need about what happened, and then possible ways to resolve it so they don't have to go searching through a number of different menus to do so. We've also provided that in kind of a customer portal where you're able to take the information out of the aircraft, post it to the web, and then go through a detailed analysis of your flight. Additionally, we've looked at several advanced onboard capabilities, like, for instance, we made a little module that you're able to do safe to land, what we're calling it flight path generation. So one of the key things to flying beyond a line of sight safely is being able to land the aircraft in case of an emergency. And that's not easy to do when you don't have a pilot right nearby. So we put together a system that at 30 frames a second are able to take a look at downward looking images, and have an example of here on the bottom, parse that up into things like roads, trees, people, cars, identify which things are hazards. So obviously you'd much prefer to land in trees if you had to, as opposed to a group of people, but ideally come up with an area that's safe to land, which for a multi-rotor is somewhat straightforward because it's usually just a point with a radius around it. For a fixed wing aircraft, you need that whole corridor to land, so that's fairly tricky. And just kind of an example of that here in a suburban environment where we show all the hazards identified, improving guesses on where to land, and then the final solution. And again, I'm kind of mentioning that because this leads into what we had to do with the hurricane work as far as advanced onboard technologies, and a lot of this work motivated that. The last one, project that we just recently got awarded with NOAA, is to do GPS denied navigation. So GPS being a single point of failure for providing the location of the aircraft is a reason for concern for beyond line of sight operations. And so we're working to add additional sensing on board so the vehicle is able to tell where it is globally without needing GPS in case that should fail. So to get onto the project at hand, this is kind of a conceptual diagram of it, but the idea is to put together a small unmanned aircraft system that can be deployed from one of the tubes in the P3, and that's compatible with a lot of the different systems that are already on board. And that's kind of one of the key driving factors to what we put together here. And I think you'll find that it ended up in a unique design, but it brought forward some of the key features that we were looking at bringing out, and that is it's fairly inexpensive. We'd ideally like to have these available to operate on several of them on a single storm and multiple of them across the entire storm season, and that it takes advantage of current technologies. There's not a lot of infrastructure change to be able to operate these, and it relies on sensors that are fairly well proven. So the heritage of this comes from the Airborne Vertical Atmospheric Profiling System, or AVAPS, that was developed starting, I think, back in '95 by NNCAR. And has been flown as dropsondes through a number of different hurricane events by several different aircraft. I even outfitted into the Global Hawk to be able to fly out many, many miles and look at the genesis of the storms. They have an impressive list of specs. I've kind of listed some of the nice things that they have here. And the nice thing about it, they've been tested over years. They're well characterized, they're well understood, and they're a great way to measure the thermodynamics of the storm, other than the fact that they only provide a column of data. Another unique thing that comes along with them is this nice radio system that's able to get a 300-kilometer range, which is great. You're able to kind of drop these out of the back of the aircraft, continue flying the mission for the manned aircraft while the dropsonde is falling through the atmosphere, and you're collecting data the entire time. So that kind of formed the basis for the design of what we put together. If you see, there's some similarities here. And the tube is basically the same almost size as the RD41 sensor that's part of that AVAPS system. And we've borrowed a lot of the sensor ideas from it as well. There's well-characterized sensors that they've put into that sonde. They've, again, been able to assemble into forecasts and things like that. So we want to build on that heritage. The idea for the aircraft is to be able to provide the low-level observations, as well as a couple of other different missions, but the key thing being able to fly to targeted areas. So being able to define beforehand a mission that it flies and return this data back to the aircraft. We're looking, even though this is a small aircraft, we're looking at 1+ hour of endurance, which significantly improves on the time you normally see as far as the dropsonde. So one of the key things to kind of bringing this technology into an unmanned aircraft system is the use of that radio interface that I mentioned before that gives you that nice 300-kilometer range. Unfortunately, it's proprietary, but fortunately for us, we have a pretty good working relationship with NNCAR, and we were able to work with some of the engineers there to grab one of the dropsondes that they'd used. And what we did is we pulled the power basically from the GPS chip, and that's kind of what I'm showing here in this image, and soldered in our own communications so that I was able to emulate the packets that the GPS normally puts out and gets injected into the radio system. And by doing so, I could change the data within that to actually put my own data in there as far as what the aircraft system is sensing. So there's a couple other different sensors on board the aircraft, related to aircraft state. And also we're doing wind sensing on board the aircraft that we need to inject into this. So by doing this, we're able to use the radio system that's already well tested, well characterized, and put our data into it. And the best thing is it's in the same packet format, the same transmission format that they're used to. So that system that I showed before that's rack mounted within the aircraft is still able to receive this data in conjunction with dropsonde data. So there's not a lot of change that has to happen on that side other than post-processing, knowing that the fields where I've injected data is not the fields that they're normally used to getting GPS info from. And NNCAR, and specifically Terry Hoek, was nice enough to provide us with a number of different test things to be able to test this. One of them is just a nice handheld radio system that takes the signals emitted by this radio and spits them out into something we can read from the computer and validate that everything's working. So continuing the work with NNCAR, we were able to come up with a design for a custom board so that we didn't need access to the IP of their radio but they were able to bring out the interfaces in a little bit easier to use way than just soldering on pins to the GPS chip. And so the picture in the middle here is the board that resulted from that. Significantly reduced size and weight over there using the entire sonde. And we have nice connectors now, so we can be able to inject those packets into the radio stream, still kind of emulating a GPS system, so none of the code needs to change. And then it also allows us to hook up to the Weissel sonde that they make use of, so that we're still getting that same quality pressure, temperature, humidity data from that instrument. Another one of the key things that we had to do was come up with a new antenna. The one that's designed to be integrated with that sonde, it's designed for it falling vertically, so it's soldered to the board, and that gives it the correct orientation. Unfortunately, with the aircraft, since it's flying horizontally and the board's mounted in a 90-degree orientation to where it's normally falling, we had to come up with a different antenna design. So using kind of the similar principles, again, trying to borrow as much as we can from previous proven technology, we came up with a design for a flexible dipole. And you can see in this slide here, this is the first prototype of it. In the lower left there, you can see a preliminary version attached to the radio board. And then on the top, you see kind of the simple assembly that we were able to come up with. This was in conjunction with a local company here, First RF, which was nice enough to work with us to develop this and test it in their anechoic chamber that they have available here. In the center, you see a tube just kind of representing the fuselage of the vehicle with the antenna deployed. And then on the right-hand side, you see it with kind of, it's within the deployment tube that we're putting on the back of the aircraft with the antenna folded down. And then in the lower right, you can see a comparison between the VSWR for the antenna for coiling it, and then after coiling it, just to show that the coiling action doesn't actually affect the ability of the antenna to transmit. Also, First RF was able to put this in their chamber with the radio and take a bunch of different measurements and compare against the DROPSONDE. Because one of the key things here is we want to maintain that 300-kilometer distance at the same bandwidth, and so we were able to prove that they matched up fairly closely. So one of the other things that we're adding to this, with the DROPSONDE, it does wind sensing, but it does wind sensing based on where it's moving in its position. With the aircraft system, it becomes a lot more complex, and we've seen this through previous efforts. This is our technical monitor, Joe Sion here, with the Coyote UAS, which kind of really got this all started. And they've done absolutely amazing things as far as sensing storms with these. And if you haven't, I'd encourage you to go take a look at some of his publications on the data that they were able to extract out of these UAS and prove how valuable the measurements of the lower part of the atmosphere near the sea surface are for determining all sorts of different parameters about the hurricane. But one of the things that was tricky was bringing out winds from this aircraft. It's a DoD heritage aircraft. It's not really designed for meteorological sensing. So while they put sensors on board, one of the things they didn't put is the ability to directly sense wind. And so they were using an estimate from the autopilot that fuses a bunch of the onboard sensors and provides you with what it thinks is the wind direction. And that didn't really result in anything that it was as close to as accurate as they wanted. So they ended up pulling out a bunch of the different various sensors from the autopilot stream. And kind of long story short, it was very difficult to figure out what the winds were based on what the vehicle was doing, just because of lag in the sensors and things like that. And the plot on the right here kind of shows that, where you can see the vehicle rolling and pitching fairly significantly because of the storm environment. And you can see that reflected on the wind speeds that it was estimating down in the lower right there. So what we're bringing to the table as far as that is our heritage in designing these wind probes. We call ours the SWIFTFLOW. It's flown on a number of different vehicles, everything from a kite, which is a pretty fun, unique application we've been looking at recently, to a campaign with use of University of Alaska Fairbanks and larger unmanned aircraft systems, our own unmanned aircraft systems. You can kind of see on the lower right there, it's been put on the side of other manned NOAA aircraft. The unique thing about this is we try to keep it fairly simple and low cost. So we're making use of new design techniques like 3D printing to be able to keep the cost down while keeping the accuracy of the probe to be fairly high. We've run this through a number of different wind tunnel measurements and characterized the probe. And what the exciting thing is, one, it not only produces good data, but then also between different probes, without having to recalibrate each and every one, they also agree very closely with each other, meaning we could save that extra cost and time having to calibrate each and every probe and be able to put together accurate instrumentation. So here's just kind of a output from wind tunnel data. This was done at the NOAA ATD facility, and many thanks to those guys for helping us out with this component of the project. But you can see here that the true output is in red, and the measured output's in blue, and it agreed, the alpha and beta and the TAS is showed here. They agree very closely with what we were setting in the wind tunnel to compare against. We've also, as I mentioned, flown this on our own aircraft. Here's an example of some process data from our S1 UAS. It's kind of a smaller aircraft that we're able to integrate up to 1 pound payload things on. That was perfect for this atmospheric science. And we were able to use this to go and grab a number of different data sets to compare against a number of different other sensors in the area and prove how accurate the sensor actually was. And I'd mentioned before, this was kind of a fun one we just did recently. This is with Jeff Bland out at NASA Wallops. We're working on a project with him to make tether sondes for balloons. In this case, it's on a kite. You can see an image in the top there, and some preliminary data. You can see temperature and then the wind vectors coming out of the bottom. So fairly versatile probe as far as wind speeds and vehicles that it can be deployed on. So what we did is we took that concept and we integrated it with this new vehicle that we're calling the S0. And you can see on the image on the left here, we made the entire nose cone into its own flush air sensing system. So by putting little holes around the front of the nose cone and then connecting those up to the pressure sensors, we're able to make the similar type probe that you saw to that SWIFTFLOW probe that I mentioned beforehand. And furthermore, we designed the cap in such a way that it tightly integrates with the electronics, getting rid of one of the common errors in wind estimation, which is sensor misalignment between the tip that you're actually measuring the pressures at, and then things like the inertial measurement unit where you're trying to get all the different orientations of the particular of the aircraft. So they're all tightly tied together, so there's very good tolerance between the two of them there. One of the big problems though with these multi-hole type measurements for making wind measurements is the mitigation of precipitation. So you can get little droplets of water that bridge the holes in the instrument, and basically make it so that you're unable to make an accurate measurement. And so one of the things we've done too with a different project with NOAA is we've looked at various different ways of mitigating that. And there's a number of different things that people have come up with over the years. We kind of went through an analysis of all of them and came up with what we thought would be a nice cost-effective way to do that for this particular project, where we're able to use mechanical interfaces to kind of mitigate whether the drops actually are able to bridge the port itself. But one of the more interesting things, and I think one of the thing we'll end up finally going with, because it doesn't actually add any extra weight to the aircraft, it doesn't add any extra materials, is taking a look at developing a machine learning algorithm to take a look at all the different data and in real time figure out when a port has been bridged. And as long as you have a certain number of these ports available, you can still make a fairly accurate wind measurement. And so since the whole idea of this project is keep it lightweight, low cost, I think that's kind of the way we're going to end up going with it. And to test that, we put together our own little test chamber. This one was kind of fun. It's just kind of a rudimentary wind tunnel, but we added to it the ability to inject droplets of varying different sizes, and we were able to change the flow on it to actually determine how many of the droplets are coming out at any one point in time. So unfortunately, the video is a little bit choppy. I know they're going to post this a little bit later, so hopefully that comes out well. And if you guys want any access to some of these videos, feel free to contact me. But this just kind of shows an overview of this droplet rig we put together. It's got the nice airflow through it, and then a module that we put in there where you're able to change droplet sizing and dispersion and stuff like that just by swapping it out. And so we use this to test a bunch of different ideas as far as, like, as I mentioned before, the mechanical integration of components that would mitigate these droplet bridging, as well as kind of components we engineered behind the inlet of the port to allow excess water to be able to seep out of the system. And so just some videos here that we put together of that testing with a flat plate that we put a bunch of the different ideas on and then kind of assessed which one performed better. All right, so we've got kind of all the sensors together for what we put on there. One of the other key things we put together was a new avionics system. Now, fortunately, as I mentioned before, since we are the ones that put together the autopilot system and all the algorithms and all the stuff, we have access to all the designs. So what we're able to do is take the design for that SWIFTFLOW wind probe and marry it with our autopilot system. And so we're able to come up with a nice, compact, relatively inexpensive design that performs all of the different functionalities necessary. And one of the nice things that comes out of this is accurate wind estimation is very necessary for performing accurate control of the aircraft. So the sensor itself benefits from the fact that that's married tightly with all the as far as the mechanical integration and stuff like that, what I mentioned before, but in turn, the autopilot also benefits from this extra knowledge about the wind environment. It's able to actually fly the aircraft better in a kind of a more tight fashion and mitigate gusts and things like that a lot better. So here's kind of an image of those avionics that we put together. Some of the key things I'll point out is that black panel, and I have just kind of like exploded view of it on the left-hand side here. We try to keep the user interface as simple as possible. Now you can hook up one of our tablets to the aircraft to be able to do some of the pre-flight planning that I'll talk about later, but we kept it as simple as possible. The top port is just for charging. There's a charge light that indicates when it's charging and when it's done charging so that you can top off these before you go and deploy. There is an on-off switch that basically just tells the system when to operate and when not to, and it'll a status light that'll blink when it's doing all its pre-system checks and then come on full when it's ready to go. And then a USB interface for upgrading firmware, changing parameters, or getting any data off for some of the interim stuff that we're doing as far as preliminary testing, because these vehicles themselves, once they get kicked out of the plane and go down in the hurricane, we're not expecting to get them back. Another one of the key things is the airframe design. And it's critical to put this together in the right way. One, to achieve obviously the mission length that we want to, but also to be able to make accurate wind measurements, and we'll kind of get into some details of that. We also wanted to keep it really simple again. We wanted to keep this low cost so that NOAA is able to deploy a number of these different aircraft for any particular storm. And we want to be able to have it again operate in the normal conditions that we're expecting to find within a hurricane, so heavy precipitation and strong winds and gusts. So we kind of started out by looking at what had been done to date, and again we're going back to the Coyote US because really that's the only vehicle that this has been done with to date, even though there are a couple other technologies in development currently to replace that. But in looking at that Coyote, what we saw is what I'd kind of mentioned before when we were talking about trying to do that wind measurement. Is the vehicle itself is not really well designed for these kind of turbulent environments. It's designed for ISR missions to go and take video of a certain location, not really to fly through hurricanes. And it comes out when we're taking a look at the analysis of a basic model we put together of the Coyote, and you can see here when we disturb it and Dutch roll, it continues ringing, and we were able to see that in the wind data. So it's critical not only for the safety of the aircraft to control, to do this design work, but also for getting good wind measurements. And so we took that with our design, we had S0, and looked at all that different stability analysis, and we're able to kind of zero in on a design that we thought kind of married all of these different desires well, as far as controllability, able to sense wind, and the endurance and performance that we're looking for. Took that and put together some initial prototypes. Again, just trying to keep this inexpensive. This was kind of a fun part for us. We were able to build the initial prototype, and you can see here just out of some foam cut wings, cardboard packing tube, and some foam tail, and actually go and get to go fly that. We started out by just flying these remote control, just so we can get some very basic data on the performance, how the airfoil was doing and things like that. And it was pretty tricky to fly. So there's a few design details that go into this, especially these tube launch aircraft. We were very constrained about the size of the wing that you could put on them, that you have to be careful to. So this kind of speaks to, again, paying attention to the design of the aircraft and how much that goes into the safety of the aircraft during the mission, and then also the ability to measure winds. One of the other things that's tricky about these smaller aircraft systems, they don't have a lot of propulsion systems available for them, and there's a fair amount of lower end solutions available for the hobby market, but nothing that was going to be able to give us the performance that we want. So one of the things we ended up doing that we didn't expect was having to go through quite an extensive analysis of all the different speed controllers, motors, props. We ended up having to make our own prop adapter, actually, because we wanted the prop to be able to be folding so it would fit within the tube, but there's not really a lot of options available at that size, so we kind of had put together our own thing. So long story short, there was quite a bit of work that went into making sure that we could achieve the performance we want as far as the climb rate and the endurance, but fortunately, after doing this long exhaustive search, we were kind of able to narrow it down into something that we liked. Our second prototype we put together, a little bit more advanced than the cardboard tube. We were looking at using a Kevlar tube for this one. We got a lot more of the surfaces 3D printed. You can see how the back section of the aircraft is this nice single 3D print, keeps manufacturing easy, simple, and reliable. And then you can kind of see in the concept on the bottom left there, the vehicle deployed and then the tube folded. And in this particular one, we also put together the ability to integrate avionics setup. And this was before we had designed the avionics, that wholly tightly integrated avionics that I showed before. So we used one of our previous autopilot systems. You can see it in the upper right here, integrated into it. But fortunately, what that allowed us to do, and during the test flight, is actually have it go fly all these patterns that we're talking about for atmospheric science. So this is showing some of the early flights that we did with the aircraft, the white being the flight path. And then in the bottom there's me throwing the aircraft, which honestly is not ideal. It'll be much better when we're tube launching these. They're fairly tricky to actually throw fast enough because these guys fly at a pretty quick pace. I think the cruise speed that we had for this one is around 16 or 17 meters per second. And so being able to throw it fast enough to be able to get it going and flying was a bit of a task. But fortunately, with the autopilot on board, we were able to do a lot better analysis. This is some of just the preliminary data from showing the commanded roll versus the measured roll. And you can see there's a bit of rigging in there that we had to tune out, but a pretty decent guess for some of the first control gains that we're putting on the aircraft. The vehicle was weighted to the weight that we expected it to be, and we actually flew the initial flight in 22-mile-an-hour winds, which kind of talks to how well the design works in fairly gusty environments. And then we also took a look at the flight performance and validated that we were going to be able to get the flight time that we're expecting. And we flew this up at Boulder, so approximately 6,000 feet. And we were able to estimate how much time we were able to get out of this, and we're looking at about 70 minutes, which meets the original design criteria of more than an hour. So since then, we've been moving on towards what we're calling more of a production type version of this one. We'll actually be deploying out of the NOAA P3, hopefully in the summer, barring whatever happens with COVID. But we put together wing molds. Now that we've kind of validated that aerodynamic design, know that it performs well. And so we're working on assembling those first articles. They're made out of carbon fiber to keep the weight down, and they'll be filled with foam for rigidity. We switched the fuselage away from Kevlar to a phenolic tube. It's a little more lightweight, still fairly robust and durable, but lighter weight, lower cost to kind of get towards those goals of having a fairly inexpensive yet robust aircraft. And then we've been looking a lot at exactly what we're going to do for the deployment CONOPS. This has kind of been most of our recent work. So as I mentioned before, we have that nice interface panel that allows you to charge it. You can hook up a USB, and the USB allows you to determine the status of the aircraft as far as it can do all sorts of onboard checks for the avionics. It'll also allow you to interface with that viceless sensor, which occasionally requires reconditioning depending on how long it's been on the shelf. So you can do that through that nice interface board that NNCAR gave us. And you could do anything like firmware updates and things like that. As far as deployment, for the deployment tube, we just decided to go with just a larger phenolic tube. We kept things simple, and we were able to purchase them for a reasonable price. You can see here the image of the S0 without its wing sitting inside the tube, ready for deployment, and then just kind of an image of the tube sitting in our office there. We based this again to take advantage of the heritage of a lot of the work that's already been done to date and make sure we can put together a system that will return reliable data and be able to go through a number of different uses without failure. We borrowed from the XBT, this kind of deployment concept where they have the larger tube that has a plastic flap. You can kind of see on the top right there that once it comes out of the tube, that plastic flap comes out. Works as kind of a drogue to pull the chute out, and then everything else is deployed from there. So just getting image capturing the CONOPS for that. The tube containing the aircraft gets pushed out of the back of the aircraft. That flap pulls out the parachute. The parachute reorients the tube. And then there's the autopilot itself is looking at what's going on with all these different conditions. And once it senses that it's on a stable configuration, actually drops off the exterior tube and deploys its wing, and then it detaches itself from the parachute module and then proceeds to fly its mission. So we were given a number of different flight patterns that were desired to fly as far as what campaigns they wanted to conduct, NOAA wanted to conduct for sampling. I've listed a couple of them here, but a lot of them require storm relative positioning. And so, to date, since they had communications back and forth with the Coyote, they were able to kind of go in and take a look, even though they put waypoint plans on it beforehand, go in and take a look what it's seeing and kind of update it. Although one of the nice things about using the AVAPS system is we get all that nice heritage as far as the distance that it can transmit all the different data, and that we know it'll work reliably and they already have the infrastructure installed in the aircraft. One of the bad things is it's transmit only. So the aircraft can't receive any information after it gets kicked out of the aircraft, which presented a little bit of a design issue that we had to work around. So the CONOPS we have right now is you're able to define a kind of a center point radius for the eye wall, since several of those different missions that I listed earlier require knowledge of where the eye wall of the aircraft or of the hurricane is. And then the aircraft's able to automatically generate its flight plan based on whatever mission you select and that location. And so that can be done on board with the interface to the aircraft or that USB port. But once it leaves there, we had to kind of figure out what to do with it at that point in time. Do we just continue to blindly follow that path? Or we thought that there could be a better way to kind of update the flight patterns of the aircraft. So we put together a fairly advanced simulator as part of this and some other projects that allows us to, most importantly, inject fairly accurate and highly detailed atmospheric models. And so working with George Bryan at NNCAR, we were able to get some data from some hurricane simulations that he'd run and inject it into our small unmanned aircraft simulation. Put that in with a model of the S0, and then we were able to generate flights through the hurricane to, not only see what we expect to need to do as far as controllability of the aircraft, but also more importantly, look at where we're driving the aircraft to for gathering the data that's going to be of the most scientific value. So I've plotted here an overview of the simulated data that we were given by George. You could just see kind of like the rain on the right-hand side. We're just showing the amount of rain in the hurricane. On the left-hand side at the top, we show the pressure associated with the hurricane. These are kind of the similar scale here. And then the bottom, I've zoomed in on the eye portion of the hurricane to show the winds, just because they'd be far too detailed or far too dense in the zoomed out view. But one of the cool things we did is we just took this simple model of a hurricane and looked at just just looking at falling isobars. So we figured if we wanted to stay centered around the area we wanted to sample, which is kind of dithering in and out of the eye wall of the hurricane, we could just simply look at the pressure that was being read on board the aircraft. So we designed a controller around that and ran it through a number of these different simulations with different starting points and different starting altitudes. And this is an example of one of the runs we did. We were able to show that, dropping the aircraft from certain locations close enough to the eye wall, we were able to get it to actually move to the edge of the eye wall and track it simply by just looking at pressures. Another thing, we're looking at adding in other different components as far as the winds and things like that to kind of better identify. But the idea is we have enough computing power on board to carry a simplified model of the hurricane, not nearly as detailed as the stuff that George has provided us with. But we think it'll be enough information to be able to actually actively update our overall mission goal, basically, and drive the aircraft to where it's going to be of the most interest and the most scientific value. So we can do things like, say, at a higher level, just track the eye wall of the hurricane and the vehicle will go and do that. So working on getting stuff together for deployment again this spring/summer, kind of the off season for the P3, so we can go kick a few of these out of the aircraft to make sure they perform appropriately. But all this is kind of coming together, and we should have these together at that point in time to be able to do some of these preliminary flights. So looking forward to that, and appreciate you guys attending the talk. Happy to share any other information about the videos and things like that if you want to contact me directly or ask the questions here as part of the seminar in the chat. And happy to share data as far as what comes out of the work that we're going to be doing this summer with these aircraft. So thank you.
Thank you so much, Dr. Elston. This was great. We have several questions that people placed in the chat while you were speaking, but I do want to point out if you do have a further question or you want to just speak to Dr. Elston offline, you can email, is it the info@bst.aero?
Yeah, that works. Or my
Okay.
personal email is just elstonj.
Okay, I will put that in the chat as well.
Sure.
But let's kick off the questions early on. So you might have to go back a few slides to refresh your memory. What is the response times of the temperature and relative humidity sensors?
Good question. I don't have that offhand, but if somebody wants to email me, like it's the Vaisala RSS 421 is the sensor. So if you want to go look that up online, it's available there, or I'm happy to provide you with the info. I just don't know it off the top of my head.
Okay, I believe someone is trying to remind you, it's between 2 and 4 hertz.
Okay, perfect.
Awesome. Okay, next question. How did you calibrate the MHP probe?
Through a number of different runs through the NOAA's ATD tunnel with the help of those guys down there. So it was, again, it's much appreciated, all the help that they put together with us for that.
Okay, awesome. Next question. I guess the question is, how does the geometry of nose of the S0 differ from the MHP, and will that make a difference in the calibration? Hoping I said that.
Yeah, it's a larger diameter. The whole pattern kind of layout, as far as the angles of the holes are out, are similar, but it's a larger diameter, and yeah, it does make a difference. So unfortunately, the S0 is small enough that we're able to get it into the wind tunnel and actually do a similar type calibration we did with the MHP with the S0 to be able to provide those accurate measurements.
We have a follow-up to that, I believe. Was that the Vaisala RS421, correct?
Correct. Yep.
Okay. Awesome. Okay, next question. From the multi-port wind module, can you compute fluxes?
Yes. I kind of hesitate to answer that already, or exactly, because we're working on projects right now to characterize how accurate that is. So we're able to measure fluxes. The MHP itself actually provides measurements at 100 hertz. So we're able to gather some very detailed information about the wind environment. And that's even 100 hertz is subsampled from what we're able to do on board. So yes, the hope is we should be able to get fairly accurate fluxes, but I hesitate to say definitively can until we have the data to prove it.
Great, thank you. I feel like you touched on this briefly, but we do have a question. How do you recover the asset after it's deployed?
Unfortunately, we don't. It's lost to the ocean, and we have looked into a few different ideas as far as making use of it after it hits the ocean. Unfortunately, communications become a little bit difficult once that happens, but we have thought about putting various different sensors where we can sense salinity or temperature of the ocean and let it sit there as kind of a buoy. So as long as the aircraft's in the area, we're able to communicate that back at least.
Great, thank you. While people are thinking of questions and furiously typing, I wanted to remind everyone, if you are a NOAA staff or contractor, the NOAA Network Libraries has a survey that I've placed into the chat. And if you could take about 11 minutes to do that, we would greatly appreciate it. If there are no questions, I'm gonna turn it over to, oh, there are questions. I knew people were typing. Okay, next one. How do you prevent or mitigate aircraft stalls during maneuvers?
We have really accurate wind information and relative wind to the aircraft information, and to prevent stall, obviously you have to deal with the alpha of the aircraft. So since we have that readily available to us and fairly large control surfaces with a fairly fast controller, it's relatively straightforward for us to be able to mitigate gusts and things like that and avoid stalls during maneuvers.
Thank you. Okay, has any research been done on recoverable zones?
Not that I know of, but I haven't really done a detailed look into that, so I'd probably be the wrong person to ask for that. Maybe Joe might be able to answer that better.
Gotcha. Okay, and to answer this question here, yes, the library has recorded this and it will be available on our YouTube channel and on our seminars website. And back to some more questions for you, Dr. Elston. How durable is it with the dramatic updrafts, turbulence in hurricane eye wall structures? Has it been in a real hurricane?
It has not. We've done that simulated data to date. As far as the durability of it, one of the nice things about these smaller aircraft is they kind of just move with the air mass. So we saw this a lot when we were doing deployment on supercell thunderstorms and even those that produce tornadoes, that even though the vehicle was translating very quickly, it wasn't seeing a lot of forces out of those because the wingspan was small enough that it wasn't seeing the high amplitude turbulence. So it wasn't seeing a lot of torque and things like that. So the vehicle just kind of moves with the air mass. So as far as like the rigidity of the aircraft, you're not seeing a lot of G loading on it. And we're specifically not trying to fly it in such a way that we're putting a lot of G loading on the aircraft.
Okay, thank you. Next question. What is the projected cost?
We're hoping for a full up material cost of just $5,000. So that includes the sensors and the aircraft and the tube and all that other stuff.
Great, thank you. Okay, we've got a bit of time still. If anyone is typing, I'll give you a minute. And Tiffany, did you want to say something?
Yes, thank you so much, Jack, for that presentation kicking off the new year. I wanted to let everybody know who's on the call. I know some people have dropped, but just let everyone know to tune in for the next NOAA Innovative Series presentation next week on February the 2nd. And you can find that link on the NOAA Central Library website, and I can post that in the chat as well.
Great, Tiffany, if you could, post that in the chat for everyone. We did have one more question pop up. Jack, you indicated you collaborated with NASA with SNOD's, I'm gonna stumble over that one every time. So it's tethered to balloons. At what height was that tested to?
So the data set that I showed was pretty low. I don't recall off the top of my head, but it was only like maybe 100 feet at most.
Okay. Well, thank you everyone for questions. If you do have a question and we haven't got to it yet, or you're typing it right now, if you get it in before I close this webinar, we will forward those on to Jack to answer offline. But if you don't have any further questions right now, Tiffany has placed that link to the library's archive page for all of the seminars. And as I said, it will be on our YouTube channel after the fact. And we have a very long question that has come in. And
Right.
since we do have a little bit of time, I'm gonna try and get through it. Okay, so John Walker is saying it was a great briefing. I understand and appreciate the complexities of pre-programming flight paths. Very interesting ideas you have come up with. Concerning the preset isobar following mode, would that be set to maintain constant altitude while following a set pressure threshold?
Yeah, that's correct. Yeah, you have to be careful that you're not changing altitudes during that, or otherwise you'll be deviating from it. So yes, it's a little more complex than I kind of went through on there as far as being able to follow the isobar. But the idea being that, yes, if you just take a slice at one altitude, you're following that particular one.
Great, okay. And the following up on that, are you concerned about rapid intensification or weakening that would cause the aircraft to move away from the eye wall?
Yeah, we're working with George to develop a couple more data sets that we can run through to kind of follow the evolution of the storm and give a couple of different examples. And then we'll run a whole Monte Carlo analysis to kind of see how robust our ideas are as far as being able to kind of update the mission. To that end too, we're kind of starting low and kind of working towards more advanced. Right now, what we're really looking to do is just kind of in real time estimate the kind of the extent and the location of the eye wall, because so many of the missions depend on that, and then kind of having the aircraft track that. And then we hope to move to more complex things where we're able to kind of determine things that have happened as far as the evolution of the storm and react to that. Ideally getting to the point where the vehicle itself just says, well, I don't know that much about this area of the storm, and it goes and drives over there to collect the most valuable data. Because, when you only have an hour to sample, it's critical that you're providing that data from the best part of the storm that you can.
Great. Following up on that as well, what about non-smooth isobaric surfaces encountered in the real world, which many models simulate?
Good question, certainly. Not something that we've looked into yet.
Great, thank you. We have a few more questions trickle in. Could this be used to 12-mile and dropped back to return to a specified location?
Yeah, you could certainly specify a location for it to end up at. As part of the flight planning algorithms, there's plenty of stuff in there from just regular aircraft systems that we put together that are all just going to go into the autopilot code here, where you can use, I kind of pointed out a few of them earlier as far as the mission plans you can put together, but one of them is just a string of waypoints that'll bring you back to a location you want to be at.
Got it. Okay, and finally, what is the utility of the UAS for tropical cyclone observations?
There's a number of papers that have described this better than I will, but basically they've run through and looked at a couple of the observing system experiments to show what happens when they try and guess the intensity and things like that, or forecast the intensity of the storm with and without both dropsonde and unmanned aircraft data. And they've shown that the targeted observations from the unmanned aircraft even exceed what happened, what they're able to do as far as accuracy of the forecast with just dropsondes alone. So if they want to contact me offline, I can provide you with references to that for people that have looked at this and are much better explaining it than I am. I'm kind of more on the aircraft design side of things.
Great, thank you. Okay, I'm out of questions. We have put that link into the chat. Sorry, Tiffany, I didn't notice that it did not go to everyone when you put it in, but I have put it in now. So if you missed this, you missed the beginning. If you wanted to just send it on to a colleague, this has been recorded and it will be on this libguides.library.noaa.gov/seminars. So if you go here, this will be posted shortly and it will be up on our YouTube channel. Ooh, someone is sneaking in one last question. With the aircraft updating its own flight plan and not able to receive information, is there risk of collision with other drones or aircraft?
Well, fortunately, since these are being operated quite a bit offshore, and the only real drones in the area will be the ones that are being deployed by the manned aircraft. So generally, what I've seen in the past, and Joe is a better person to answer this question, but what I've seen them do in this past is kind of spread out where they're doing dropsondes. They haven't done multiple unmanned aircraft per storms yet, but with the AVAPS system, it'll support up to 4 simultaneous connections, and so per radio setting. So you're able to fly multiple aircraft and get all that data back. As far as collisions, they're not really sharing that information with each other, so it'll be purely up to the design of the mission, but it's a big airspace. And honestly, I think if you're sampling, you're going to probably want to either stagger them as far as spatially around the storm or at different altitudes or things like that, so there'll be a natural separation between the aircraft.
Great, thanks for that answer, Jack. Okay, and it made sense to our asker. Thank you. Okay, everyone, you have Jack's email right up here at the top of the slide here, info@bst.aero. I've also put Jack's personal email into the chat as well. And with that, I want to thank you all for joining us today for NOAA Innovators. And please tune in, as Tiffany said, next week for our next Innovators series. Thank you, everyone.
Thanks, everybody.